We are going to work some of the more difficult of the gas laws problems. So we will go through the combined gas law, the ideal gas law, as well as Dalton's partial pressures. What we won't go over is Boyle's, Charles, or Guy-Lussac's gas laws, because those can be derived from the combined. So if you can do the combined, you can pretty much figure out how to do the rest of those. Alright, so I was nice and told you that this was in fact the combined gas law problem, but if you ever are stuck on a problem and you're not sure which equation to use, look at what you have and see if you can label that. So I'm going to underline, I have a 5-liter sample, okay, I know that's a volume because it's in liters, of hydrogen, which has a pressure of 1200 torr, so I'm going to label that as a pressure. What is the new pressure? Okay, so I know I'm looking for P2. If the temperature is changed from 150 Kelvin, so this is my T1, to 250 Kelvin, which is my T2, and the volume is changed to 10 liters. So this is my new volume. I'm going to go back and label that as my initial volume and my initial pressure. So now that I'm looking at the problem, I can see that I have initial and a final pressure I'm looking for, initial and a final volume, initial and a final temperature. So that should, in your mind, signal you to use the combined gas law, which is P1 V1 divided by T1 equals P2 V2 over T2. So now all I need to do is fill in numbers and solve for my missing, which the question tells me is the second pressure, so I'll be looking for that one. P1 is 1200 torr times V1, which is 5.0 liters, divided by my initial temperature, which has already been converted to Kelvin. That makes my life a little easier. And pressure 2 I don't know, so I'm going to leave it as P2. But my new volume is 10.0 liters, and my new temperature is 250 Kelvin. So now my task is to get P2 by itself and my other numbers on the other side so I can solve the problem. So to get P2 by itself, I am going to multiply this side by the inverse. So 250K over 10.0 liters. This way 250K cancels and my liters cancel. Whatever I do to the right side, I have to do the left side. So I'm going to come over here and I'm going to do the same thing. 250 be multiplied across the top, and 10.0 liters will be multiplied across the bottom. So in order to solve this, I'm going to multiply across the top. So now my problem looks like this. 250K times 1200 torr times 5.0 liters divided by 10.0 liters times 150 Kelvin. So multiply across the top, multiply across the bottom, divide the top by the bottom, and you should get 1.0 times 10 to the third, and I am looking for pressure, so that means our pressure is in torr, and I can look at what units cancel. And I'm left with torr. And that is my final pressure. Alright, again, I'm telling you this is the ideal gas law, but let's work this problem as if we didn't know so that we can figure out how to approach these problems on a test or a worksheet. So, I want to know what the pressure is, so my pressure is unknown, of a 0.500 mole, that's my N, of CO2 in a 5.00 liter, tells me its volume, container, at 150 degrees Celsius, that's temperature. So, looking at this, it looks like I have the ideal gas law because I have pressure, volume, temperature, and moles. The ideal gas law is PV equals nRT. So I have all of these, but right now I have two unknowns. So I have to commit to memory that R is a constant, and for our purposes it's equal to 0.0821, and the units are liter atmospheres per mole Kelvin. Because of that constant, I know I need to change my degrees Celsius into Kelvin. So 150 degrees Celsius plus 273 gives me that same temperature in Kelvin, which is 423 K. So now all I need to do is plug in my numbers and solve for my unknown. I don't know pressure, so I'm going to leave my pressure, times the volume, which is 5.00 liters, is equal to my number of moles, 0.500 moles, times my constant, 0.0821 liter atmospheres, mole kelvins, times my temperature in Kelvin, which is 423 K. So now to solve for P, I'm going to divide both sides by 5.00 liters. And so now all I have to do is solve the problem. I'm going to just double check my units and make sure that they cancel. So here we have moles on the bottom, that will cancel. Liters cancels, and Kelvin cancels, leaving me with atmospheres. Because I'm solving for pressure, having a unit of atmospheres makes perfect sense, so I'm doing it right. Your final answer when you multiply across the top and divide by the bottom should be 3.47 atmospheres.